Good morning, my YouTube viewers. In this video, we're going to study some more R programming in Google Colab. So if you want to use Google Colab to write a program in R, then what you do is you type in this code into your browser, which is https://colab.research.google.com/notebook create equals true and language equals R. And what that will do is that will enable you to use your Jupyter notebook with Google Colab in R. So I've done lots and lots of notebooks in Python, and so I decided it was time to move into R. And the reason why is because a data scientist needs to know both R and Python because they use both R and Python. One of the good things about R is it has a lot of functions built into it already. And because it has functions built into it already, you don't have to use a lot of libraries. But there are libraries in R that you can use if you want to. It's something called lots of libraries in R. But what I'm going to try to do for the time being is just use R's inbuilt functions so you can get a feel of those. And then after you've got a feel of R's inbuilt functions, then you can start using the libraries that are common to R. So what we're going to do is we're going to analyze the Nile dataset, which is annual measurements of the flow of the Nile from 1871 to 1970. So we're going to call the Nile dataset up using data brackets Nile, and then we're going to get the class of the Nile, which is TS, which lets you know it's a time series. We're going to get the structure of the Nile. The structure of a Nile is a time series from 1 to 100 from 1871 to 1970, and it gives you all of the readings of the Nile for 100 cells of data. So the start Nile is 1 for 1871, and the end Nile is 1 for 1970. So in 1970, it has only one reading, and so that's going to make it a little bit problematic when we make our box plots, but I'll show you how I got around that. So we're going to view the Nile, and you can see that the Nile is a time series, and it has 100 cells of data. I checked the length of the Nile, and the length of the Nile is 100. So what we've done is we've made a scatter plot of the Nile. So Nile plot brackets Nile, comma, main equals Nile annual measurements. XLab is year, YLab is annual measurements. Type is P, that lets you know it's a scatter plot. PCH is 19, and color is blue. So we're going to add a linear trend line. Model becomes LM, that means linear model, brackets Nile. And I think that's a tilde, time Nile. AB line, brackets, that's going to be your red line. Model, comma, color equals red, comma, LWD equals 2. And LWD is line width. And then we're also going to put a grid on it. So this is what the scatter plot looks like. So it doesn't look like much to go on, but what you can see, quite vaguely, just quite vaguely, that as time goes on, the measurements decrease. And you can see that quite vaguely because you can see that the red line is sloping down. And you can see that just quite vaguely, you can see that the values are less at the end than they are at the beginning. So we're going to do the passenger, the Nile. That's Nile measurements. So you can see here that the Nile measurements decrease every year. So now we're going to do a line plot. So, and the color is going to be purple. And you can see just very vaguely, as time goes on, the measurements of the Nile just slightly decrease. So now we're going to check the Nile measurements from 1960, from 1871 to 1970. And we're going to do that and color that in pink so you can see the outliers and where the bulk of the data is between around 800 to around 1,000. And the interquartile range is going to be around 900. And you've got your outliers as well. So now we're going to convert this inbuilt data frame into a standard data frame. DF becomes data.frame brackets year equals floor times Nile, measure equals s.numeric Nile. So you've got your head, you've got your year, and then you've got your measure, and then we've got the tail, you've got your year, and you've got your measure. So we're going to do a box plot for every year. So box plot brackets and measure, I think it's a tilde, comma, year, comma, data equals DF, xlab equals year, comma, ylab equals measurements, comma, main equals Nile measurements by year, comma, color equals light blue, last equals 2. And you can see that these box plots are so tiny that it actually looks like a dot. So because you get a box plot for every year. So now I decided that since the box plots are so tiny that what I'm going to do is I'm going to break the data set down into decades. So DF $decade becomes floor brackets DF $year divided by 10 times 10, and then you got your head. So now you've got your new data frame with a year, a measure, and a decade. And then what I wanted to do is, because there's only one value in 1970, so I wanted to drop the last row of the data set so that one value in 1970 didn't get a box plot. So DF no last becomes head brackets DF comma -1. That means you're getting rid of the last row in the data set. And then you've got your DF no last. And then so and then now what we're going to do is we're going to plot the measurements for each decade. Box plot brackets measure tilde decade comma data equals DF no last comma xlab equals decade comma ylab equals measurement comma main equals measurement per decade comma column equals light green last equals 2. So now you have the measurements per decade with the last decade ending in 1960. And then if I didn't remove the last row of data, then it would have given you a box plot for 1970 with only one cell, and that didn't look very good, so I didn't want to use it. So you can see that from the decades, the box plot for every decade, you can see that it's also gradually going down as well, for every decade. So now we're going to break it down into half centuries, because I just wanted to get a little bit clearer perspective about what actually is going on with the Nile. So DF $half cent trade becomes if else brackets DF here becomes 1920, comma 1870 to 1920, comma 1921 to 1970. So now we have another data frame. You've got year, measure, decade, and half century. So you've got the tail of that. So you can see the first part of it is 1871 to 1920. And then the second part of it is 1921 to 1970. So now we're going to plot this for every half century. So box plot, black brackets, measure, tilde, half century, comma, data equals DF, comma, X lab equals half century, comma, Y lab equals measurement, comma, main equals measurement per half century, comma, column equals yellow, LAS equals 2. So you can see the plot here, and you can see more clearly that in the second half century, the measurements were significantly lower than the first half century. And then so it might be a little bit more difficult to pick this out when you're measuring it by year, and a little bit more difficult to pick it out when you're measuring it by decade. But when you measure it by half century, you can see that the second half century is less than the first half century. So I did actually ask Copilot because I thought this was to do with global warming. And this is Copilot's response is, the decreased flow of the Nile is partly linked to global warming. Human factors such as overuse, dam construction, irrigation, and water management policies also affect the decreased flow of the Nile. So the decreased flow is partly due to global warming, and it's partly due to human factors. So that concludes this video. We've covered the data set of the Nile, which is an built-in data set in R. And thank you for watching this video. If you like my video, please like and subscribe, and I will be making some more R-related content for you in the future.